Hey everyone, let me start with a simple thought. Have you ever noticed that sometimes fixing a tiny inconsistency can change the entire game? That's exactly what Maxwell did for physics. He looked at Ampere's law and said, wait a minute, something doesn't add up. We already know a steady current produces a magnetic field. But what about when the electric field itself is changing? Shouldn't that also produce a magnetic field? Maxwell boldly proposed that yes, a changing electric field must generate a magnetic field. This little addition explained how radio waves, gamma rays, and even visible light could exist. And all of this started with the humble charging capacitor. In its gap, the electric field changes continuously even though no conduction current flows. That's the mystery Maxwell set out to solve. Before we fix the law, let's recall Ampere's original version. It says, the closed line integral of B dot dl equals mu naught times the conduction current I as function of time. In simple terms, closed line integral of B dot dl equals mu naught times I of t. This means the magnetic field depends on the current enclosed by our loop. This worked beautifully for wires and coils carrying steady or even time-varying currents. But the moment we tried it inside the gap of a capacitor, problem. The conduction current there is zero, so Ampere's law predicted no magnetic field. Yet experiments showed the opposite. Clearly, something was missing. Alright, let's test this on a parallel plate capacitor connected to a time-dependent current I of t. Suppose we want the magnetic field at a point P just outside the plates. To make life easier, we choose a circular Amperian loop of radius r around the current. Now, by symmetry, the magnetic field must be the same at every point along that circle and tangent to it. This is like tracing a hula hoop around the wire. Every spot on the hoop feels the same magnetic tug. Neat, right? So now we can apply Ampere's law and see what happens. Here comes the math. Ampere's law says closed line integral of B dot dl equals mu naught times I of t. For a circular loop, the left side becomes B times 2 pi r. That's because the loop length is its circumference, 2 pi r. So we write B multiplied by 2 pi r equals mu naught times I of t. Rearranging, we get B equals mu naught times I of t divided by 2 pi r. And there we have it. The magnetic field at distance r depends on both the current flowing and the radius of the loop. This makes sense physically. The farther you are from the current, the weaker the magnetic field gets. Just like how the sound of music fades as you walk away from a speaker. Let's dig deeper with a worked example. Imagine a capacitor of plate area A being charged by a current I. What's the displacement current between its plates? Step 1. From Ampere's law, we already know B multiplied by 2 pi r equals mu naught times I. So, B equals mu naught times I divided by 2 pi r. Step 2. In the gap, the electric field is E equals Q divided by epsilon naught times A, differentiating with respect to time and noting that dq by dt equals I, we get displacement current density J sub d equals epsilon naught times dE by dt, which equals I over A multiply by area A, and voila, I sub d equals I. So the displacement current in the capacitor gap is exactly equal to the conduction current in the wire. Isn't that beautiful? It means no matter whether you're inside the wire or in the capacitor's gap, current continuity is perfectly maintained. So let's wrap up. Ampere's law alone wasn't enough. Maxwell added the missing piece, the displacement current. A changing electric field acts like a current and produces a magnetic field. The modified law, called the Ampere-Maxwell law, ensures it holds true everywhere, in wires and in capacitor gaps. This idea isn't just a patch for capacitor problems, it's the cornerstone of electromagnetic wave theory. Because if electric fields and magnetic fields can chase and sustain each other, then waves can travel through empty space, and light itself turns out to be an electromagnetic wave. Isn't it amazing how one tiny correction changed the course of physics forever?